And that is why to make them permanent magnet, we consistently make them aligned for a very long period of time, and hence they become permanent magnets. So what we are talking about is the concept of electromagnet. Okay, now the metals, now can you see these two diagrams? In this one, all the domains are in random directions. The domains are shown to you in terms of capsule. All of these are in random direction, but like this, okay, this rectangular capsule. But when they are placed in an external magnetic field, or if I stroke a magnet in same direction time and again, I'll keep doing that. Suppose this is my magnet, and over this material I'll keep doing this. I cannot go like this and then this. No, I have to keep going in the same direction time and again. What will happen? All the domains will get inclined towards same direction, and this will result me a magnetized matter. So I'll read it. The metals affected by magnetism consist of tiny regions called domains. This point is very clear to us, which behave like tiny magnets. Normally they are arranged in the magnetic materials, all pointing in different directions completely, but if they that is why they cancel out each other effect. But by some means, if we can make their directions in the same one, then they are going to exhibit a net magnetic property, and then the so-called material will be a magnetized one. This is what, and this is how magnetism comes into matter. Classification of magnetic materials. So when we are doing so, suppose there is this element, there is this element, there is another one, okay, and I am trying to magnetize each one of them individually by the same process. Some materials can get the magnetic properties very easily, and they can sustain with those magnetic properties for a long period of time. Some materials cannot get any magnetic properties even for the slightest bit, and they will not retain it. Obviously they are not getting, how will they retain it? Some materials might get it fast, but they will not retain it. They lose their magnetic properties as soon as the external factor is avoided, as soon as external factor is taken out of the picture, right? So these are diamagnetic, paramagnetic and ferromagnetic materials. Diamagnetic, the diamagnetic substances are those in which the individual atoms or ions do not possess any net magnetic field of their own. So one thing is clear in diamagnetic, okay, dia, para and ferro. So their individual magnetism is not there in diamagnetic. They do not possess any net magnetic moment of their own. When such substances are placed in external magnetizing field, they get feebly magnetized. So these things, the magnetic domains are not existing first of all. But even if we can make few magnetic domains by placing them in an external magnetic field, they are get feebly magnetized. That means there will be very few creations of magnetic domains, and it will exhibit magnetic property, but that will be very, very, very slight. Okay. Next one. Wait. The important point is, if such materials is placed in an external magnetic field, they get feebly magnetized in a direction opposite to the magnetizing field. Well, this is a rare feature. They will not get magnetized in the same direction as of magnetizing field. They will get magnetized in opposite direction. Next one is paramagnetic. Paramagnetic are those in which each individual atom or molecule of ion has a net non-zero magnetic moment. So they have non-zero magnetic moment, and when substances are placed, they get feebly magnetized. This one also gets feebly magnetized, even though they already have the magnetic property because of the magnetic domains present, but they get magnetized in the direction of magnetic field. So what can you say about the last one, which is ferromagnetic? The ferromagnetic will be, they have net non-zero magnetic moment, and they get strongly magnetized and all in the same direction. So diamagnetic as ferromagnetic are those in which each individual atom has non-zero magnetic and they get magnetized in the same direction, right? Now, what is hysteresis curve? This is the last topic of this chapter. To understand hysteresis, first of all, I'll explain you in terms of cycle that everything, there are a lot of reactions like reversible reactions or electrification, de-electrification, magnetization, demagnetization. There are a lot of phenomena in physics in which something happens and we take it back. Some energy is given and we take it back. So these form a loop, a continuous cycle of loop, and these loops are studied, and based on their graphs and their energy involved and energy expelled, we come out with some sort of conclusion. So basically this is also a curve. This is a relationship between magnetic field strength and magnetic flux density. So magnetic field strength and magnetic flux density, these are two different things. BH curve. This is B, which is magnetic flux density, and this is H, which is magnetic field strength. Now the difference is the H, which is magnetic field strength, this is the applied magnetic field. I have a sample, it is neutral sample. In terms of magnetism, it is neutral, it has no magnetic properties of its own, and I want to magnetize it. So what I am going to do, I am going to place this thing in the magnetic field, and I let magnetic field pass through it continuously. So what will happen? Consequently, all the domains which are forming will get inclined in the same direction, and it will possess the magnetic field. That is simple, right? So this magnetic flux density, which is B, this is the amount of magnetism which has been inculcated in this sample. So you need to understand the difference between them. This one is the magnetic field strength, which is the magnetic field applied on this sample, due to which it is going to get magnetized. This thing is the strength up to which, or its own magnetism, which has developed due to this. Sorted? Now what happens is, everything is at 0 now. I'll start increasing the applied magnetic field, right? So magnetic field is increasing, and the body will start possessing magnetic properties. Basically all the domains are getting inclined, and it will start becoming a magnet. So the graph goes like this, and it will ultimately come to saturation point. Why? Because all the domains have got inclined in one direction. Now nothing more can happen. We cannot make it more stronger, because already all the domains have inclined towards the direction of this applied magnetic field. So it is a magnet of particular strength. I cannot increase the strength. Even if we start increasing the magnetic field further, the domains are still there, which are already inclined, so it will not increase its magnetic flux density. That means its strength. That is clear? So I'll remove this part. Sorted? So at some point, at particular point, it gets completely magnetized as per its nature. It might be very strong, it might be feebly strong, it might be very weak, anything, but according to its own character. Now till that point, I got from here to here, I was doing it very interestingly, but I got bored. So I thought, okay, let me demagnetize this stuff again. So in order to demagnetize, what should I do? I'll remove the magnetic field. So that means I started decreasing the magnetic field which was applied by me again. I started decreasing the magnetic field, and I saw a fall in its magnetic properties. That means its magnetism, or the strength, or its magnetic strength, in simpler words, it also started decreasing. So the magnetic strength, when it started decreasing, it came to a point when this became 0 back. I initially went in this direction, I am decreasing it. So when I completely vanished the applied magnetic field, this graph came to this point. That means there was this much magnetic property still left in the sample. That means not all the domains which were magnetized by applied electric field got fall back into same position. Some still left, and that is why it is still exhibiting some, though very small, but some magnetic property of its own. So this is called residual magnetism. Residual magnetism, or in simpler words, it is called retentivity. Alright. So now the word is clear. Retentivity is basically residual magnetism. Now I was surprised that, okay, even if I have completely zeroed the applied magnetic field, I still got some residual magnetism in this sample. So what should I do to make it completely neutral as it was before? I'll be applying a negative magnetic field. So initially that is why, because when these sort of domains were there, I applied magnetic field in this direction to make them all inclined in the same direction. But now I have vanished this magnetic field, and some of them have left and others are still fallen back to same position, but some are still there which is exhibiting this residual magnetism, and to remove that I am applying a negative magnetic field, due to which what will happen, they will gradually fall back to or tend to be in a random direction before getting originated on the opposite side. In the meantime, it will be somewhere 0. So when I started increasing the magnetic field in opposite direction, the residual magnetism came point to 0, and this field, this much part, is called coercivity. So coercivity is the negative magnetic field which must be applied on the sample, which can remove the residual magnetism part or which can remove the retentivity, is called coercivity, right? Now this was intrigue, it was interesting. I thought, okay, now I have completely made the sample neutral, though I have to apply some opposite magnetic field to make it neutral. Let me continue this process on the opposite side. What will happen? I continued this process on the opposite side and again saw that it has come to a saturation point, because all the domains which are there got inclined in the same direction, but this time in the opposite one as compared to the before one. And again, when I reverse the magnetic field, first of all, when I zeroed it down, there was some retentivity, residual magnetism, and then there was coercivity. So this graph will keep on following the same path over and over again. It will not come to 0 from where we started. There will be some retentivity or there will be some coercivity. The study of these graphs is called hysteresis, magnetic hysteresis curve. Okay, now I'll read from here. The relationship between magnetic field strength, which is this, and magnetic flux density will follow a curve up to a point where further increase in magnetic field, will result in no further change in flux density. It got saturated. This condition is called magnetic saturation, which I was telling you, till a point. After that, the plotted relationship will follow a different curve back, because this graph was not followed, it was followed by this point. So this relationship will follow a different curve back towards zero field strength, at which point it will be offset from the original curve by an amount which is called remnant flux density or retentivity, or basically residual magnetism. The thickness of the middle describes this much, describes the amount of hysteresis related to the coercivity. So this part is coercivity, which was the residual magnetism getting 0 by applying opposite magnetic field, and this is our graph, right? So this is BH graph, which we study to know what type of materials can be used for what type of formation. For example, I have shown you two graphs, one is of steel, one is of soft core, so soft iron. So steel is used in making permanent magnets. Why? Because permanent magnet should have very strong magnetism, it should have strong residual magnetism. So see, the amount of retentivity is high and amount of coercivity is also high, because we want strong magnetic field to nullify it. In soft iron core, we only want high retentivity, we do not want coercivity. So this is why the graph is a bit steep. So the study of these kind of graphs gives us a brief idea about how various types of materials can be used for various purposes. So this is all in this chapter. The magnetism concludes here.